Hello, welcome. My name is Christian Kaczynski. In this video, I will show you an example of finding the limits of a sequence.
An example, you could say, authentic, which students actually worked on at the University of Mumbai in the fall of 2019. For help during solving the example, we will ask our mathematical friend Kiwi. So let's get started. Let's look at this example. What do we have to do there?
I chose this first example here.
Here it is. In the middle, we have mysterious 3 dots. This means it is not a finite sum. By increasing n, which is the number of terms in the sequence, we add more terms. When it comes to limits in general, also, and regarding the method known as the Squeeze Theorem, or there are many other names for it, I won't be showing it to you from scratch here, because I covered it in my course. Limits, and there I show exactly how it is with these limits and demonstrate this method from the very beginning. Here I will only focus on solving this example. If anything is unclear, I invite you to my course. Let's go. We will apply the Squeeze Theorem. In the Squeeze Theorem, we had to take this sequence whose limits we need to calculate. Here it is. No, I'm not writing the limit here, the sequence, just the sequence without the limit. So there's no limit here. And this sequence had to be bounded by some sequence from above, some sequence from below, and show that this upper sequence and this lower sequence converge to the same number, to the same limit. And intuitively we sense that if something is bounded from above and approaches something, and something is bounded from below and approaches the same thing, then what is in the middle will also tend to approach that. I discussed this in detail in my course where I invite you. And now I will immediately get to the constraints, like how to limit it from above. So we are looking for something, some sequence that will undoubtedly be greater than this one, have larger terms. Each of its terms will be greater than the corresponding term of this one. So we are looking for something greater. It will be something like this. Look, each component of this sum is undoubtedly smaller than the one on the right, and the one on the right is larger. Why? Someone might ask, how is that? After all, the numerators are the same, and the denominators here are larger. Here on the left they are larger, right? Here the denominators are smaller, definitely. Here it's +1, +2, here, well, +0, actually everywhere, right? It's just in squared. Why is it supposed to be greater? Because each component here has a smaller denominator, and when the denominator is smaller, the whole number is larger. Look, 1/2 is greater than 1/3, or 1/3 is greater than 1/10. The larger the denominator, the smaller the entire fraction. That's why these here have smaller denominators. So each of these fractions is greater than its corresponding one. Well, undoubtedly, since each fraction is greater, the entire sum is also greater, right? What will we limit from below? Following the same path method here, we will increase the denominators here, without a doubt. On the left, each denominator n squared plus n squared plus n is greater than or equal to. In the last one, it is equal but greater than or equal to the corresponding denominator in these fractions. Because n is the term number of the sequence. The term number of the sequence can be 1, 2, 3, 4, and so on. And here it ends at n, meaning n here is the largest component it reaches. So here each fraction has a larger denominator, meaning each fraction is smaller. So without a doubt, this is smaller than that. So we have bounded this sequence, bounded it from above with such a sequence and from below with such a sequence. Now just calculate the upper limit, the lower limit, and show that they are equal. So let's go. The upper limit, this one, a common denominator, right? So it will be n plus n plus n plus n, n times, because here it is n times.
This n repeats at the top, actually.
Well, that's n times n. And here we won't even involve Kiwi in this, right?
N times n is n squared. N squared over n squared is 1, simply. Easy? Easy. The lower bound is like this, common denominator like this, n plus n plus n times, so it's n times n. And here maybe, although it's not a difficult limit, we'll ask for help from our Kiwi.
Let's go, Kiwi.
There was such a limit.
On top, it was n times n times n, and at the bottom, n squared plus.
Oh, such a limit uncalculated on the top. N times n is, of course, n squared. Are we right, Kiwi? We are right because Kiwi signals us in green. The method of factoring out, I assume you are already familiar with it. I also discuss it in my course.
On the top, there's nothing to factor out. On the bottom, I factor out n squared. Is that correct, Kiwi? It is. N squared and n squared cancel out.
I'll make a mistake for fun, okay?
So I'll simplify. Instead of 1 over n, I'll simplify it to 1, making a mistake in the process, but let's give Kiwi a chance to shine. He's bored. Try slowly, try again, or let me help. Help me, Kiwi. Where did I make a mistake? Give me a moment, I need to think. Think, old man, think, no problem.
So Kiwi told us here how it should be 1 plus 1 over n. No? It should be not 1 over 1 plus 1. So let's correct it. As you said, Kiwi, it should be 1 over n here, right?
That's how it was supposed to be, and it is.
So it's 1 over n approaching infinity. So 1 over n approaches 0 for reasons I provided in the course.
So we are left with 1 over 1, which is 1, and the limit is calculated. Thanks, Kiwi. Bye.
I enter this result, 1.
And now a very important part of the task in the theorem of 3 sequences is writing the answer at the very end.
At the moment, you don't have the answer. Your task was to calculate the limits of this sequence, and you calculated some other one and another one. But here, you need to clearly tell the professor that you understand what this is about, right?
And write the answer, refer to something.
And you refer to the power of the squeeze theorem.
The limit of this sequence which you were supposed to calculate equals 1. And now everything is clear by virtue of the squeeze theorem or using the squeeze theorem or however. That's it. Thank you very much.
I invite you to my course. Thanks to Kiwi too.